Calculus, video 44, related rates, example 3. Go ahead and pause the video, write down the question. Okay, so suppose that a right triangle has legs x and y and hypotenuse z. If leg x is increasing at a rate of 2 centimeters per second, at what rate must z be changing to keep the area at a constant 60 square centimeters when x is 8 centimeters? Okay, let's draw a picture of what's happening. So we're starting off with a right triangle. Legs x and y, hypotenuse z. So down here I've drawn a right triangle. It has legs x and y. It has a hypotenuse z. Draw something like that. What we have is that x is changing. In fact, x is increasing at a rate of 2 centimeters per second. So x is getting bigger. That means the triangle is changing. X is getting larger, but if you look down at the bottom, at what rate must z be changing to keep the area at a constant 60 square centimeters? So this triangle has area 60 square centimeters. X is getting bigger. That means that the shape of the triangle must change a little bit. And now maybe you have this triangle, but still the same area. That's probably too small of a triangle, but you get the point. The area should not be changing even though x is increasing. That means z might also need a change. And if z is changing, then it will be changing at a particular rate. Therefore, you'll get a dz dt. Okay, that's the idea. Let me erase the green here. If I can. There we go. Okay. So let's just start writing down things we know. If x is increasing at a rate of 2 centimeters per second, that means we know that dx dt, the rate at which x changes, is 2 centimeters per second. Positive or negative 2? Positive 2 because the x is increasing. Okay, so dx dt, positive 2 centimeters per second. I want to know how is the hypotenuse changing. What is dz dt? Question mark. I don't know how y is changing, so I don't have a dy dt. I know I want to ask this question eventually here when x is 8 centimeters. Although at this point it's a variable because it's changing. And the big important part here, we are keeping the area constant at a constant 60 centimeters squared. So area of the triangle is 60 square centimeters. That part is not changing. It's going to be a constant. It does not get a variable. Okay, so since I want to know dz dt, and I do know dx dt, what I need is an equation that relates x and z. That way I can take the derivative implicitly and get a dx dt and a dz dt. So, what equation relates x and z? I'm seeing Pythagorean theorem. I'm seeing x squared plus y squared is equal to z squared. That is an equation and it relates x and z, and I like that. But we have a problem. The problem is, if I took the derivative right now, I would get 2x dx dt, that's good because I know dx dt, plus 2y dy dt equals 2z dz dt. Now that's good on the dz dt because I want to know that, but I have this extra dy dt in here that I don't know. That's two variables, it's one equation, that's not a good thing. So what I want to do first is to rewrite this equation only with x's and z's. I want only x's and z's, no y's. So in order to do that, I need another equation. I need an equation that relates y to one of the other two variables. Equation that relates y to either x or z. That way I can substitute whatever y is equal to in for y. Like say it's like 6x, right? If y is 6x, I can put 6x in place of y, and now I just have x's and z's. Okay, thankfully, we were told that when we change the x, the area stays constant. We can use that, hopefully, to relate y with one of the other variables. So area of a triangle, area, maybe I should kind of use some more space down here. Maybe over here. area of a triangle. That is 1/2 the base times the height. Or in our case, the area is a constant 60, is 1/2 the base is x, and the height is y. All right, this is what I wanted. This is an equation that relates x and y together. So since I don't want y's in my other problem, I want to solve for y here. So I get 120, you multiply both sides by 2. 120 is equal to x times y. Y, therefore, dividing both sides by x, y is 120 over x. Okay. I can use that to plug into this y here, and then I'll just have x's and z's. All right, well, actually, y is 120 over x. Y squared is, what's that, 1440 over x squared? Yeah, 14,400, sorry, 14,400 over x squared. So actually, I'm going to replace y squared with 14,400 over x squared. And my new equation looks like this. X squared plus 14,400 over x squared is equal to z squared. Or because I know I'm going to take the derivative, let's rewrite that as x squared plus 14,400 x to the negative 2, bringing that x squared up to the top. That's x squared there, is equal to z squared. Side note, complete side note, it's not a bad idea to start writing z's with little lines through them. That way your z's and your 2's look different from each other. Okay. Now we'll take the derivative. So x is a variable because it's changing. Z is changing, it's a variable. All this with respect to t. So when I take the derivative, I need to use the chain rule. I get derivative of x squared, that's 2x dx dt. Bring in the middle term now, the 14,400x to the negative 2. Bring the negative 2 down, so it's minus 28,800x to the negative 3 dx dt is equal to 2z dz dt. Don't forget that extra dx dt right there. That's one people often forget. Okay. We could just plug stuff in. Actually, well, you could divide all these terms by 2. Maybe that'll make life a little bit easier. Or you could just plug in from right now. Let's just plug in. All right, I've got 2x. X, if you remember, was 8. Dx dt, how was x changing? X dx dt was 2 centimeters per second. Minus 28,800 divided by x cubed, 8 cubed. I just moved that x to the negative 3 back down to the bottom, 8 cubed, times dx dt, that's 2, equals 2 times z. We don't know z, but maybe we can figure it out in a minute. And dz dt, right, which is what we're looking for. All right, so all looks good, but I need to find out what z is equal to. Need to know z. Need to know z. All right, let's see if we can figure z. When x is 8, right? So now we're plugging in when x is 8. So we can use the fact now that x is 8. And we can't do Pythagorean theorem yet because I don't know y or z. But back over here, right here, I see y is 120 divided by x. Well, if y is 120 divided by x, then y, when x is 8, is 120 over 8. 15. Y is 15. Okay, that told me what y is, but it didn't tell me what z is. But we can go back to the Pythagorean theorem now. X squared plus y squared is equal to z squared. Because we're talking about when x is 8, right? So we've already taken the derivative. So when x is 8. So from that, we get from x squared plus y squared equals z squared. 8 squared plus y was 15. 15 squared is equal to z squared. 64 plus, that's 225. Is equal to z squared. 289. Actually, I think this is a Pythagorean triple. Square root of 289, I believe, is 17. 17 it is. Z is equal to 17. The Pythagorean triple 8, 15, 17. It's like 3, 4, 5, right? It's a Pythagorean triple. It is the sides of a right triangle. It could be 8, 15, 17 for the hypotenuse. Anyway, z is 17, so I can go back now. I can plug 17 in for z. Let's see, 2 times 8 times 2, it's 4, it's 32, minus 28800, 28800 divided by 8 cubed times 2. I'm getting 112.5 is equal to 2 times 17 times dz dt. 32 minus the 112.5, I'm getting negative 80.5 equals 34 dz dt. Divide by 34, and dz dt, the rate at which z must change in order to keep that area constant, about negative 2.37. Let's just call it negative 2.4 centimeters. I believe we were in centimeters per second. So in order to keep the constant area, if x is increasing by, I believe it was 2 centimeters per second, yep, then z must be decreasing by negative 2.4 centimeters per second.